Hello everybody, I want to welcome you to the Open Sputnik project presentation. I'm glad that many people want to see this presentation, so hopefully I can fulfill your expectations. So basically I will separate in two parts. I will first talk about the hardware level and then about the infrastructure. Hannes will do the second part. So I will first introduce you basically in the low level. Can you turn it to your phone? Just, it's too loud. Just. Okay, better? Okay. If you have any questions, please wait till the end. We'll have at least a quarter hour for questions, and hope I can ask you the questions. You can ask the questions later. This is, by the way, Hannes with the second part. The hardware was actually done by me and my wife, Welte, and Harald Welte helped us a lot with the firmware and did some nice low power features for our firmware, so this is where Harald comes in. Okay. I'm basically a freelance hardware software developer. We have a small company which basically consists of me and my wife. I'm focused on deeply embedded systems, so basically the lower it is to the hardware, the better we like the project. Since a year or so we are into RF design, RFID technology. Maybe some of you know already our second project, which is this OpenPCD RFID reader for 13.56 MHz. And we did things like being able to read this electronic passports that are currently available throughout the world. And we are, for example, able to get the JPEG information out there and stuff like that. And it's a really low-level design, so it's great if you want to learn something about the previous generation of RFID technology for 30.56 MHz. You can actually see the waveforms and modulate it, and you can put it out on several headers, and you have connections where you can sniff data. And we also have a project which is not fully released yet because we didn't manage to finish it in time, which is the OpenPICC project, which is meant to emulate RFID tags also for 13.56 MHz. So basically the hardware is done. What we're currently working on is anti-collision. It's not programmed yet. And this design will be also available as open source. Basically, what we're talking about in this particular case for the Sputnik devices, we came to the conclusion that it doesn't make much sense if you want to cover big areas to have passive tags. So we decided to have actively powered tags to reduce the reader costs and to allow bigger coverage with very low cost readers. So therefore we decided to build more expensive design more expensive tags that have active battery on them, and therefore able to actively transmit higher ranges. We distributed currently around 25 readers throughout the BCC. You maybe see some of these black boxes with the rubber antennas on it fixed mostly on windows and in the room 1 at this ventilation system. Maybe you have seen them already. To keep the design as simple as possible and to have good access to real-time data, the readers we distribute are actually very stupid. So they just pick up the data that is transmitted over RF interface, which contains the tag ID and other information. I will talk about this in more detail later. And just forward the packet to a central server where the data is gathered. We're currently already logging the data, so we can later, if we found better algorithms, we can post-process the data and find out the tracks people took through the Congress. And to keep the load on the readers as low as possible, we decided to use UDP because we need less memory and have much shorter latency. So basically, if a packet is picked up at one reader, it will arrive in a few milliseconds at our aggregator, which further distributes the data. Hannes will talk about the real-world protocol, which you are able already to access, which contains an XML representation of this low-level data. And the basic idea is we try to place the readers. So in most cases, at least 2 readers will pick up a signal. And we have a possibility to get limited strength measurement. I will talk about this later too. So we can roughly estimate the position. So basically, as soon as we detect, we know who we are and naturally what your favorite color is. We can analyze, we hang often together in the same areas, and if we do this to all 4 days, then we get a pretty good picture about the relations between groups of people. And we can do such nice internet shop features like show me the guys that visited similar talks as I visited. Okay, let's have a look at the tech architecture. Basically, to keep the costs very low, we use this ugly PIC CPU. The only advantage was that you can buy it directly from Microchip without going to dealers, have them pre-programmed at a low cost. So this made basically the decision, and you can choose from a wide range of low power devices. All the magic is done in this NRF24L01, which is the HF frontend, and you definitely want to have a look into the data sheet if you're interested in architecture. This chip is very great. We like it very much. It provides high-level features like automatic CSC check. It provides handshaking, multiple pipes. Each tag can have multiple MAC addresses. You can decide which of the MAC addresses is a broadcast address. So, because we have access to this reader and we have this in-system program interface, you can reprogram the software easily. We will release the code during that day on our website for the text firmware, but there is one minor problem. We wanted to show that we can contain this tracking information so we have full power over it. So for example, in case one of you guys have a GNU radio device or a similar device which is able to sniff the data on air, you will see that you see nothing. Because the data is encrypted, you basically see only random chunks of data flying around, and the shared key is kept at the tag and at the aggregator software. So the readers only stupidly forward the encrypted data without knowing if it's correct or not. But it's checked at the reader, and if it can decrypt correctly, then it's a valid packet. We have also CSC checksum with an encrypted packet. I will also talk about this later. The point is that naturally the first thing if you have such a device and you see that you can receive and transmit data, you think immediately about meshing. But because in such a large scale like we are currently, we thought that it's too dangerous to introduce a meshing protocol in the first place, because we don't know how it will scale at such a high amount of people having these tags. So there is no meshing currently included, but we included this 32 kilohertz watch crystal that enables you to wake the device up at a well-defined time. So you have a possibility, for example, to add a time slot based anti-collision and stuff like that. So meshing, I think, with this hardware is possible. The other information I think is not. Okay, what's also interesting, in the top right part you see a silver part of the tag, which is the touch sensor. And basically it's working based on resistance. Unluckily the impedance is too high, so if you touch it, it will stay pressed for say 10-15 seconds. But the idea is that a flag is then transmitted within the data and signals the server that you have a request to the server. So some kind of simple intercom mechanism is possible with this hardware. And the whole device is powered with this 3-volt lithium coin cell. You can get them easily, and We haven't checked the current lifetime because we added the encryption, which adds more CPU load, so the device doesn't sleep that long because the computation takes some time. So currently, yesterday I looked it up on the oscilloscope, and what I saw was basically the wake-up time between the sleep intervals is basically around 20 milliseconds. This is the time it takes to compute the new packet with the correct encryption, which is basically XXTA, this time encryption algorithm, the extended version, which makes sure that the neighbors of the data count into the encryption. So if you change basically one bit in the original data, then the whole packet is completely different. So there are around 19 rounds XXTA runs over the data. Okay, so the front end provides 2.4 gigahertz. You can configure it up to 2 megabits. This results in 2 megahertz wide spectrum. But if you want to have more channels, you can configure to 1 megabit and it's 1 megahertz. And you can use up to 128 channels. The allowed channels are only, say, 82 or so in practice. So you're not supposed to use channels above 82 for your applications. The lifetime with the tech version without encryption was 6 to 8 weeks, constantly transmitting every 1.5 seconds. So the only disadvantage on this approach is that it's 2.4 gigahertz, which is unlike the exact resonant frequency of water, which is mainly the body consists of. So this, the body effectively blocks the signal. So this means that if you look towards a reader, you have directly line of sight. You get obviously perfect connection, but if you are turned back to the reader, then the signal has to travel through your body, and then the range is cut down by 50% approximately. Okay, then open air, we see ranges between 20 to 40 meters. It only depends how you hold it, if you hold it freely or if it's attached to your body. And for example, in a real-world environment or flat, where we have small rooms with drywalls which traveled through to 2 drywalls and which resulted in roughly 10 meters range through walls. If you try the tag, you will see that if you press it firmly to your body, then the signal vanishes to practically nothing because the antenna gets detuned. So if it's loose somewhere on your jacket or somewhere, there's the best position where it has some minimum range from your body. So 1 centimeter or so is optimal to get the best distance. And if you hold it freely, then you can easily get this 40 meters range. Already talked about this, that every tag and every base station can receive and transmit. Currently the tags are only transmitting and the base stations are only receiving, but it can be swapped simply. So basically you already found out that the ID that is printed on the back side of the tag, we program it into the device. So basically this is your user ID, which is basically some kind of number that only is assigned to you. Okay, so we roughly transmit once per second. We said that we want to keep it simple and stupid. So we decided to do a probability-based anti-collision. So what we did was that the ID you have printed on your tag feeds a pseudo-random number generator, and then it sleeps the random time. So you see that the pulses you see by when blinking LED, that it's not equally spaced in time. So the times change, and if you get a collision, then the probability is high that the next tag will survive. And because we have 2 megabits, we have a very short on-air time So for example, I tested a little 400 tags. I programmed 5 tags to each to transmit 90 packets per second, and I got only a packet loss of 10%. So even if 400 tags are on a very dense space, then you still get practically no collisions because of the high bitrate. Okay, the LED flashes during transmit, so it's a function control. And for getting the position of your tag, we use a feature of the chip which allows us to transmit data at 5 different power levels. Level, we transmitted the data. So the idea is that if you have a reader and you receive a packet that was transmitted at a low power, you know that you are near to the reader. And if you only receive the highest level packets, then you know that you are high, you are far away from the reader. That was the basic idea, and the ranges, the 5 ranges you have available, scale linearly. So one more range is at least twice the range, and one higher power level is roughly a fifth more in terms of range. And just to be sure that you get tracked even in harsh environments, we decided that every second transmit is not the cycled power level, but the highest power level. So it cycles through all power levels, but every second packet is the full power packet. So one cycle roughly takes 10 seconds or so. Okay, so we have a tag ID in the packet, the power level used, flags, for example, button press, and to make replay attacks impossible because someone maybe could see your tag ID or so, and can capture a packet, for example with new radio, and can replay it somewhere else, so you can clone you virtually. So to disallow this, we have a constant counter that counts at each transmission, and in the server software there is a piece of software that throws away all packets with sequence numbers before the sequence number you currently saw. That's our only idea how to get rid of the cloning. And because the packet is encrypted, you are not supposed to clone packets. So, but if you find a possibility, we want to hear about it. I already talked about this. It's this XXTEA, design encryption algorithm for encryption. It nicely fits into the firmware image. We have only 3.5 kilobytes of flash, so we had tight constraints. And to make it possible that you people can change the firmware, we decided to program in high-level language. So I know that for big microcontrollers, they are not well optimized for high-level languages, but it definitely is, in my opinion, scales better if everyone can contribute to the project when high-level languages are used. So all the code is in C, so and currently it's completely stuffed up to the limit of 98% or so, but for your own test, if you do your own protocols, you can throw away the encryption and you have 60 or 70% free flash, so there is plenty of space for additional applications. And there was one problem we found out that if you pull out the battery, then it isn't supposed to start at 0 again, because then you will be regarded as a cloned user. Therefore, every time you unplug the battery and replug it, it will start at the next code block. So the next sequence ID after replugging the battery will be higher than the last ID received. So you can unplug and replug the battery 6500, 65536 times. And then it stops working. We decided to limit it there. The read architecture was a problem. Basically, it's a spin-off of another project I created. So it was just cheaper to copy it. So unluckily, the reader architecture currently has no power Ethernet. You maybe saw this botched up self-made power Ethernet injectors we created, the mechanical ones you see the readers hanging down. And another disadvantage is that it's a proprietary CPU, this UBCOM 2022, which is in fact a pretty nice CPU because it provides up to 2 Ethernet ports. You can directly connect it to magnetics, you don't need any PHY, and they are pretty cheap, around 12 euros or so. But the disadvantage is that this software development kit for this is awfully expensive. It costs around 2,500 euros. So in my opinion, it doesn't make sense to make an open source project out of this. So if we see that there is demand for this solution, we want to create a reader based on the Atmel 32-bit controller, which is much better than this ugly 8-bit architecture. And we will finish it, I think, within the next year. We already use this controller for our own PCD reader, so it's a very cool architecture where you don't have to pay any money at all to get started with development if you want to build your own reader, because it can be programmed from scratch over USB interface, and then you have no trouble. But in case someone's interested, this reader provides a UDP shell. It can be enabled, and then you can have a textual interface where you can transmit stuff, receive stuff, so you can fully operate it remotely, the reader. And basically, it escapes all the functionality that this high-frequency front end allows. Okay. This is the current architecture. We have all the tags, then this distributed readers, and as I said, the RF interface is already encrypted. The encrypted packets are just forwarded to the aggregator, which collects them. There we do binary logging, so as soon as we find our proper algorithms to narrow down the position in a better way, we can post-process the data and provide, at any step, we improve the algorithms. Better estimations. Currently, we can only see which reader picked up the signal and in which strength. And this data is already there. You can connect to HTTP, Sputnik, Congress, this is CDE. We never tried it, how it will scale, so it can be that if now 5 people connect to it, it will be badly crashed, but it can also be that it will survive far more users. We haven't tried it yet, but I think we'll find out in the next hours and days. For your convenience, this ugly binary data is converted to XML, and the basic idea behind it was that if you find any nice algorithms, you can plug into this XML server, get the XML stream downstream, and you submit your data estimations back, which can be distributed to other users again. So you can, from outside, plug into the system and make external plugins which provide better estimations or another information that is currently maybe not provided or connected with, for example, other tracking possibilities. We did some tests in the last weeks how you can estimate a person's position without having to lie about the position that we obviously can't trace it easily because it depends on how the person is turned. For example, if you be in this room and you just make a 360-degree turn, then obviously it will look for the readers that are you running around because the data is, if you turn towards the reader, data is strong, and if you turn away, it gets damped by your body. So what we found out is that what is very important is the negative knowledge that is available. For example, obviously, if you are near a reader and the reader can't see it all, then you're not there. But this information can be combined in multiple ways. We can, with one reader, we can already combine these two values where we transmit the maximum, where we receive the maximum level, but where we don't receive the lower level. So basically, it's this yellow area where we can estimate the person is. But if you don't see transmission, you are not in this, but this can be, here it is, combined with the other. So in this particular case, you picked up the yellow band, you estimated the position, but you know that the other reader hasn't picked up the signal at all, so you can cut this part away, and what remains is the yellow part. So this is the position where the person can be. And if you have multiple readers, you can narrow down the multiple possibilities that are available to a very few points where a person can be. But usually it's the most simple way to just put one reader in a room or two readers, so because you have the shielding of the walls, then you're pretty sure that the person is inside the room. So you can do stuff, for example, if you have an office and you want a call routed to a room where you're actually sitting, you can do this easily asterisk, I guess. You just, if you pick the signal up, you just say in this room, I only have a look at the low power levels, because I don't want to get the high power levels from next room to the wall. And if you get this, you know the person is in this room for sure, and you can easily make applications like call is routed to the room where the person actually sits. Okay, so we wanted to have this device regarded as a generic interface for transmitting data over RF interfaces. For example, if you have two tags, you can create a base station easily for it, because you have I/O pins available on the programming pins, and you can stream the data out you receive. For example, you can configure one of the tags as a receiver, and it will pick up the tag data from other. And then you can easily create your own access point that will run on a PC actually. But you have to use, for example, the easiest possibility in my opinion is to use this RS-232 level converters, and you only have to do a software UART in the tag that will just transmit the data without any feedback. And then you have an access point application for only the 10 or 12 euros, which the 2 additional euros make for the UART. So what is also possible, because you can very quickly change the frequencies within 100 microseconds or so. So you can quickly jump by your own scheme between the 80 available channels. So you can hide yourself from being picked up by most frequency analyzers, because the on-air time would be very small, and if you have your own scheme where you jump through all the channels, you can use the watch crystal to make sure that it jumps at the perfect time. Then you can hide it from sniffing, because on each channel it will only appear for, say, a millisecond or so, or less. We want to thank to many members of CCC Berlin and friends of ours that helped us with programming these all devices. We had 1,000 devices that had to be programmed manually. And for example, Artcom decided to make this great 3D presentation of the Congress, which will make this solution less geeky but more interesting, where you see people actually moving. You have the surveillance cameras. You can display content, information for the person, that you can get information to your tech basically. So other persons can touch on the touch screen, and there will information window pop up with the information you provided, which you are free to decide what information you provide to us. And members of CCC, for example, designed this nice logo for it, and basically Sputnik is yours, and you decide what to do with it. And I think we will fix our technical problems with displaying the data, I think during that day or till tomorrow, so it will be visible already. But you can already access the stream on the address I indicated, and you can track persons you know already with simple applications like grep and so on. We will distribute a floor plan where you see which tag ID is where, because currently you have only a list where hundreds of picked up signals are flowing by, and you don't know which reader picked it up. And the graphic representation, which shows you which reader is where, so you know where the person actually is, will be released during the next hours. So then you can at least information where you can say easily, for example, tell me if person A enters this in this room. So this can be easily done. And you can already register yourself on the same machine. This is sputnik.congress.ccc.de. And enter your user information at our desk. We are able to we can combine your tag ID with the information you provided with your account. So we want to make sure at least a bit that only person that is responsible for the tag can update it. And now Hannes will talk about the more interesting part, what can you do with the data and how it will look like.
Good day. I'm Hannes Minner from Chaos Computer Club Berlin, hacker, Doom hacker. I will talk about Sputnik middleware and visualization. Well, visualization was done by Attendees. Harald will talk about it. So the problem I will cover is the middleware, so that piece of software. So we have here the RFID, the access points, which are talking UDP, Milosch provided, and the middleware doing XML and talking to the visualization. So the basic design goals was that I receive some UDP data, UDP frames from the access points, convert them to XML, add some position information because the visualization needs to have positions to position their avatars. And have a web interface for for correlating users to tags. So the UDP datagram looks like that. There's first the originator, so the sending IP address of the base station, then how big it is, which protocol version used, then there are some flags, there's ACK, but more especially the button pressed flag. Then we have a byte of transmit strength, that's the transmit strength used by the access point. Then a 4-byte sequence number and a 4-byte tag ID. So that's basically what I'm parsing, and as interfaces, I have an XML stream at Sputnik Congress CCC.de on port 8000. It submits and receives observation with a given priority. So we have a priority level in the XML stream. So if you get /0, you get all raw information, all raw UDP frames converted to XML without any position information, only with who has sent the UDP frame. On information level 24, which is currently not available because we don't have yet the position data of the observers, you will get later observation with singularized position data. And then there's a web interface for user tag correlation and overview. So the XML we use on the XML stream is observation. We have an observation, it has an ID, it has an observer, so who has seen this observation, an observed object, which is the tag ID or a URL with the tag ID, then a time, it's a double float encoded seconds.microseconds, then min-max distance, which are float values and which is a transmit strength translated to a float. Then a direction vector XYZ, which is currently not in use. then a priority that's 0 or 24 or 23 or whatever. Then optional position, so at level 0 you don't get any position information, but at level 24 you will get position information. Yeah, for the HTTP interface to get some useful data out of the tag ID, you can simply get at HTTP Sputnik Congress CCCDE/tracking users, and you get back an XML stanza. So you get back a tracking user response with the values anyone entered. So an ID, a name, an email address, a nick, a mugshot URL, a sex, and a role, and which talks he visited, and unknown visitor tag ID if there's no person, no user correlated to the tag ID yet. The same is true for observers. You can get /tracking observers, where you get back a list of observers with an ID, position, name, and type. Yeah, and basically the following applications are done by me. It's a position singularizer, which subscribes to the XML stream at level 0 and uses the observer data to add position information into the observations. Then a pentagraph matcher, which parses the pentagraph database and correlates if a user is 10 minutes in a room where a lecturer is, that the user has visited the lecture. Then also a room lookup, so in which room the user was or wasn't the last time. And now I wanted to have a live demo. So I will just turn it to Sputnik. Okay, that's a live demo. All this stuff is written in an object-oriented, high-level programming language called Doom. So no C here, no buffer overflow C. So that's the live stream, what you currently see. You see observations from the observer, which his ID, which objects he currently sees, then a timestamp, a priority, min distance, max distance, and the direction. Direction is always 0 currently. And also, that's the basic stream that's at level 0, so no position information yet. And the other thing is that one. That's the web interface. Once you connect, you get a list of users, a list of observers, a list of tags. So no observers yet, we have to fill in that. And here are some tags, and if I log in, users, so now I can edit a tag and correlate it to a user. So let us say that is Fuba 23. Sounds okay. That was that. XML stream is on port 8000. Okay, and then I will switch over to Pavel, who will talk about the visualization. Yeah, okay.
Yeah, okay, just a couple of words regarding the visualization you can see downstairs. We choose to set up a virtual observation camera setup. So we have a 3D model of the DCC, which was provided by Martin, who was working on this model for years, I think. And we took the model and exported it in our proprietary XML format for our Y60 engine, and did write this application mostly in JavaScript with a few C++ modules to handle the avatar billboards. So we tested it with up to 1,000 billboards that can move simultaneously in the world, and hopefully this should work. We'll see. Okay, just a couple of words regarding why we did use this engine. First of all, because we know it, and it's an engine that is done to do special applications in a very short time. So actually, it's more 3D multimedia framework, and I think it took roughly, I would say, the order of 10 to 15 days to put everything together you see down there. Yeah. How does it work? It's quite simple. You've seen the HTTP stream. We just parse the stream, and if we see a new tag there, we create a new avatar. If a known tag is observed with position information, we animate the avatar to move to the observed position. So what you will see down there then is a lot of moving around, because we do randomize the positions within the estimated area. If a tag is not seen for some time, in our case 30 seconds, then we silently remove it. We have a touchscreen interface down there where you can select virtual cameras. I think we have about 30 virtual cameras which look like or act like observation cameras, and we can select one and sweep it and look into all the different rooms, and then all the avatars running around are pickable, so you will be able on the touch screen to pick an avatar, and then it will retrieve the information associated with the tag ID if there is one, and also display the talks you have visited. Okay, so thank you very much, and all you have to do now, if you haven't done it already, buy one or more of these tags. I think it's fun to have more of them, to play with them, create your user ID, and come to visit us on our booth and get your tags associated. Thank you.